Namaskar. In this lecture, we are going to study the new concept or a new definition of subsemigroup and submonoid. Okay, these are as similar as the subgroup. Okay, we will know about the group theory. So, as similar subsemigroup as similar as a subgroup. Okay, so first of all, the definition of subsemigroup. Let S star be a semigroup and let T be a non-empty subset of S. Here T is the non-empty subset. Okay, remember this. If T is closed under the operation star, or we can say that T satisfy closure property for the binary operation star, that is A star B belongs to T. Okay, whenever AB belongs to T, if we consider two elements from the set T and the and A star B belongs to A star B also belongs to T, then we can say that T is closed under the binary operation star. Okay, then T star is called a sub-semigroup of S star. Okay, this is very simple definition. S star be the semigroup. T is a non-empty subset of S. And what is our condition? T is closed under the operation star. That's uh, that's done. Okay. So then T star is called the sub-semigroup of S star. Similarly, submonoid. What is the definition of submonoid? Let A star be a monoid with identity element E. What is the monoid? Monoid is the semigroup with identity element. Okay. So A star be a monoid with identity element E. And let T be a non-empty subset of S. Okay. If T is closed under the binary operation star, that is A star B belongs to T whenever AB belongs to T, and identity element also belongs to T, then T star is called a submonoid of S star. Okay, same definition. Sub-semigroup, S star is a sub-semigroup, T is non-empty subset and T is closed under addition. Similarly, for submonoid, S star is a monoid, T is non-empty subset of S, T is closed under addition, and one more condition for the monoid is the E is the identity element also belongs to T. Okay, so these are the simple definition of sub-semigroup and submonoid. Now note, there are some note. Observe that the associative property holds in any subset of a semigroup, so that sub-semigroup T star of a semigroup S star is itself a semigroup. What it says? If we consider any subset of a semigroup S star, then S star satisfy the associative property. So this subset also satisfied associative property. So T is subset of S star. T is subset of S. So T also satisfied associative property under this binary operation star. Okay. So sub semigroup T star of semigroup S star is itself a semigroup, because the semigroup is non-empty set which satisfied associative property under the binary operation. Okay. So T is here non-empty subset of S. S satisfied associative property. So T also satisfied associative property. Okay. So T star also semigroup. So in simple, we can say that every sub semigroup is itself a semigroup. Okay. In group theory, we says that every subgroup is itself group. Okay. In vector space, we says that every subspace itself a vector space. Okay, similarly every sub semigroup is itself a semigroup. Okay, similarly every submonoid of a monoid is itself a monoid. Okay, every submonoid is itself a monoid. Okay, this is simple. Now let us see some example. Example number 1, this is the trivial sub-semi group. Okay, if A star is a semi group, then A star is a sub-semi group of A star. Okay, every group is subgroup of itself. Similarly, every semi group is sub-semi group of itself. Okay, so here S star is a semi group. So S is non-empty set. Okay, it is known from the definition. Then it is known that every set is subset of itself. So S is subset of S. That is, S is non-empty. So S is non-empty subset of S. First condition is satisfied. Also, A star is a semi-group. So A star B belongs to S whenever A comma B belongs to S. As star is a binary operation. Binary operation means map from S cross S to S. So A star B belongs to S for whenever AB belongs to S. Okay. So we have a S is non-empty subset of S, as well as S is closed under the binary operation star. Okay. Hence S is closed under the binary operation star. So S star is a sub-semi group of S star. Okay, this is very simple. Similarly, let S star, second example, let S star be a monoid. Then S star is a sub-monoid of S star. Okay, same solution. Solution is same as above, but here S star is monoid. So let E be the identity element of S star. Okay, every monoid is a semi group with identity element. So consider E be the identity element. Then E belongs to S. It is clear. And S is subset of S. Okay, because S is non-empty subset of S, and as see earlier, S is closed under the binary operation star. Okay, we see in this example. So S is non-empty subset of S. S is closed under the binary operation star with identity element E belongs to S. Okay, so S star is submonoid of S star because it satisfied all the condition to be a submonoid. Okay, now the third example is, let S star be a monoid, and if T is equal to singleton identity, where E is identity element, then T is equal to singleton E. Okay, then T star is also submonoid of S star. Okay, what we will show that, we will show that T is non-empty subset of S. It is clear, and T is closed under the binary operation, and identity element itself belongs to T. So T is a submonoid of S star. Let us see. Here T is equal to singleton E, and S star is a monoid. Okay, so it is clear that T is non-empty subset of S. Okay, it is clear. Also T is closed under by operation star S. E star E is equal to E belongs to T. Okay, hence T star is submonoid of monoid S star. These are the simplest example of sub-semi groups. Okay, or submonoids. Now, sub-semi group generated by an element. If we have a given any particular element of a semi group, then we can generate sub-semi group from this element, as we generate cyclic group from the some element A. Okay, so this is similar to cyclic group. Okay, we generate cyclic group from from the particular element. Okay, similarly, so let us see. First of all, defines the power of an element. Okay, so let A star is a semi group and let A belongs to it. we have considered particular element A from the set S. Okay, we define power of a raised to n recursively as follow. Okay, for n belongs to z plus is equal to set of all positive integers, that is equal to n, set of all natural number. Okay, so a raised to n is equal to a for n is equal to 1. Whenever n is equal to 1, then we get a raised to n is equal to a. This implies that a raised to 1 is equal to a. Okay, and a raised to n is equal to a raised to n minus 1 star a for n greater than equal to 2. Okay, this is the we define the power of an element. Now, moreover, if S star is a monoid, if S star is monoid, then it is semigroup with identity element. Okay, then we can define a raised to 0 is equal to identity. Okay, in our general algebra we define any element, any number raised to 0 is equal to 1. Similarly here in group or in semigroup we define a raised to, in monoid we define a raised to 0 is equal to e. Okay, now if m and n are non-negative integers, then a raised to m star a raised to n is equal to a raised to m plus n. Okay, where mn belongs to z plus union 0. Okay, or we can say n union 0. This is simple. Example number 4. If S star is a semigroup where A belongs to S and T is equal to set A raised to I belongs to Z plus, then T star is sub-semigroup of S star. Okay, for any given set it is necessary to show first of all it is non-empty subset of S, and then after we show that T is closed under binary operation star. Okay, so let us see solution. Here S star is a semigroup. Okay, T is equal to A raised to I belongs to Z plus. Since it is clear that T is subset of S, okay, because T is generated by the element of set S and set S is closed under the operation star. Okay, binary, because it is the binary operation. So all these element belongs to S. So T is non subset of S. Now we saw that T is non-empty. For that consider 1 belongs to Z plus. Okay, for 1 belongs to Z plus, A raised to 1 is equal to A belongs to T. Okay, so we get one element A in T. Okay, so T is non-empty subset of A star. Now we saw that T is closed under binary operation star. So consider two element A raised to I, A raised to J belongs to T. Okay, now A raised to I star A raised to J is equal to, we apply this formula. Okay, A raised to I plus J. Now I and J both are integer, so sum of two integer is also again a integer. So A raised to I star A raised to J is equal to A raised to K, where K is equal to I plus J belongs to Z plus. Okay, so A raised to K belongs to T. This implies that A raised to I star A raised to J belongs to T. This implies that T is closed under the operation star, because we have considered two arbitrary elements from T and product of these two element also belongs to T. Okay, so T is closed under the operation star. So T is non-empty subset of S and also T is closed under the operation star. So T star is sub-semigroup of S star. Okay. Example number 5. If S star is monoid, A belongs to S and T is equal to A raised to I belongs to Z plus union singleton 0. Okay, then T star is submonoid of S star. Okay, let us see solution. As similar process, okay, as we have discussed in the example number 4, the same process we will follow in this example number 5, but here there is only one change. Here S star is a monoid, so we get identity element E in S, and then after we saw that this identity element also belongs to T. All other process are same as example number 4. Okay, so here S star is monoid. S star is monoid. Let E be the identity element of S star because S star is semigroup with identity element. Now T is given is equal to set of all element A raised to I belongs to Z plus union singleton 0. Okay. Since it is clear that T is subset of S as we have discussed before. Okay. T is subset of S and for 1 belongs to Z plus A raised to 1 is equal to A belongs to T. Okay. So T is non-empty subset of S. Also for I is equal to 0. This is also okay. For I is equal to 0, A raised to I is equal to A raised to 0 is equal to identity. So A raised to I is equal to A raised to 0. This is the form of the element of T. But this form will give us identity. So identity E also belongs to T. Okay. So we get identity E belongs to T. Now we saw that T is closed under the operation star. Okay. So let consider two element A raised to I, A raised to J belongs to T, where Ij belongs to Z plus union 0. Then A raised to I star A raised to J, product of these two elements is equal to A raised to I plus J. This is equal to A raised to K belongs to T, where K is equal to I plus J belongs to Z plus union 0. Okay, set of sum of two non-negative integer is again a non-negative integer. So K is also belongs to Z plus union 0. Okay, so we get two arbitrary element from T and product of these two element also belongs to T. So T is closed under operation star. Okay, so T is non-empty subset of S. T is closed under operation star. Also identity element E belongs to T. So T star is a submonoid of monoid S star. Okay. So this is example number 5. Now let us move to the example number 6. If T is the set of all even integers, okay, T is set of all even integer, then T cross is a sub-semigroup of monoid Z cross. Here Z is set of all integer, okay, T is set of all even integer. Our aim is to show that T is sub-semigroup of monoid Z cross, where cross is ordinary multiplication. Okay, but it is not submonoid of Z cross. So we solve it. Here Z cross is monoid. Okay, Z is set of all integer with binary operation addition is monoid. So 1 is the identity element for the multiplication. Okay, so Z cross is monoid with identity element 1. Okay, now T is set of all even integer. This is equal to set of all even integer we can write as a set of all 2n, where n belongs to Z. Now it is clear that T is subset of Z. Okay, because here it is also these are integers. So T is subset of Z, as well as for 1 belongs to Z, 2 into 1 is equal to 2 belongs to T. So it is very simple to show that T is non-empty subset of Z. Now consider two element AB belongs to T. Okay, we are going to show T is closed under the multiplication. So consider two arbitrary element AB belongs to T. Then AB belongs to T and the element of the T is of the form 2n. So there exist two integer m and n belongs to Z such that A is equal to 2m, B is equal to 2n. Okay. Now A cross B is equal to 2m into 2n is equal to 4mn is equal to 2 into we want to consider the formation like this, 2 into some integer. Okay, so 2 into 2mn is equal to 2k, where k is equal to 2mn belongs to Z. So this is we have considered k as an integer and 2 as it is. Okay, so the form of A cross B is like 2k. This is the form of T. So 2k belongs to T. Okay, so for A and B are two arbitrary element of T, and we get A cross B is also belongs to T. So it says that T is closed under binary operation, under the multiplication. Okay, so T is non-empty subset of Z, also T is closed under the multiplication. So T is closed under multiplication, that is multiplication of two even integers again a even integer. So T is closed under multiplication as well as T is non-empty subset of Z. So Tx is sub-semigroup of Z cross. Okay, this is cross, not X. Okay, this is the multiplication sign. But now sub-semigroup is done, but 1 is not even integer. Okay, 1 is odd integer, so 1 does not belongs to T, that is identity element does not belongs to T. So T has no identity element. If T has no identity element, then semigroup we cannot say it is monoid, because monoid is the semigroup with the identity element. So here T has no identity element, so we can say that T cross is not submonoid of Z cross. Here it is monoid, but its subsemigroup is not monoid. So it is not necessary that every subsemigroup of monoid is again a monoid. Okay, so this is enough for this lecture. In next lecture we will discuss about the isomorphism of subsemigroups or semigroups. Okay, thank you.